So now, in order to compute the average lifetime, so then n is going to be equal to 1. This is just the nth moment. I have to compute the total population of the bound state times Tn and then evaluate the integral. I can also look at the fluctuations. So the total population will be population of the LR1 and LR2, two states. And that one, if I write down using this model, if I now write down ordinary differential equations, this will be two coupled ordinary differential equations, okay? And luckily, because they're linear, I can solve them analytically exactly without any numerical work. And then so this is what I did, and this is what I found. So these are experimental values, some of the experimental values that I took from the Nature paper, and then these are my graphs for the average lifetime. That's the solid graph, solid line, and then for the fluctuations, this is the dashed line, and it looks like this, okay? And of course, I played with the parameters. I played with the parameters so that I'll have a good fit between the theoretical curve and experimental lifetime points, okay? And if you look at the distribution of lifetimes, at 10 piconewtons, at 2 piconewtons, it looks like this. If you apply 5 piconewtons, the distribution of lifetimes looks like this. Then 10 piconewtons, it goes like this, but then at 20, it comes back. So it's a very strange lifetime dependence on force, actually. And if I do it for the monoclonal antibody, I just recover, just the sleep behavior. I don't have any catch behavior, but I recover the sleep behavior as they observed in the experiment. And I also have these fluctuations here, okay, at around some force. So this is what I have done, and these were the results. And then by doing this repeated fitting, what it looks like is that in the absence of force, this is K10 is much faster rate than K20. So basically, there's much larger probability to die out from this state than from this state. And the transition from this state to here is 8 times faster than the transition from this state to this state. So basically, most of the time, the ligand receptor complex, in the absence of force, exists in this LR1 state. Sometimes it exists in LR2 state. And I was also able to estimate the distance between the minimum and maximum along the reaction coordinate for unbinding from state LR2, that's 1.1 nanometer, and then from state LR1, that's 1.5 nanometer, and then the difference between these two distances is 5.5 nanometer. That's a huge difference. In biology, 5.5 nanometer, that's a huge difference. And I'll show you simulations from which it will be obvious why there's such a huge distance between these two states, okay? So I also played with the landscape for p-selectin G1, that's monoclonal antibody, okay? That the molecule, the control molecule. And what I found was that Y1 is equal to Y2, 0.32, R20 are equal to R10, 10 inverse seconds, K10 is equal to K20, 0.35. So basically, you have just one state. Because these parameters were so close, you basically have just one state. So you have, when this molecule binds to p-selectin, the unbinding landscape, the energy landscape is just basically one state, okay? When this molecule instead binds to p-selectin, you have different landscape. You have completely different landscape. So this is more biologically relevant landscape than this one, okay? So in reality, in nature, you have this landscape, okay? So, and there's a huge difference between PSGL1 counter receptor and anything else. It will be completely different landscape, okay? So that's one of the main conclusions. So now, and you can think of catch sleep in terms of the, phase diagram, okay? So you have phase 1 where you have only catch, and then you have phase 2 where you have catch and sleep, and then in phase 3 you have sleep bond. So you have catch bond and sleep bond. And right now everybody's talking about catch bond and sleep bond. Number of papers discussing this has been increased. I would say by by a factor of 10 or 20, because they have found this is not the only pair of molecules that exhibits catch-sleep behavior. They found at least 10 more in bacterial systems, what have you. And, we're thinking of writing one more paper because they're not referring to our paper anymore. So we want to remind them that we were the first who came up with this model. People are brutal. In biophysics, people are brutal. They refer to your paper 3-4 times. 5 years after, they don't remember you anymore. They refer to their own papers. So we want to come back and write one more review article so that they'll keep citing us. Okay, so, you can show mathematically that, if you have in this force regime where you have this transition, you can think about the unbinding rate in terms of effective unbinding rate, which is a sum of two components. One is this one, the other one is this one. When you have force below 3 piconewtons, this guy is basically 0. You can neglect it, and then you have this one. So you can think about K catch, the kinetic rate for catch bond. And then once you exceed 15 piconewtons, this guy becomes smaller, and then you can think about the kinetics of unbinding in terms of the kinetic rate for sleep bonds. Okay, in a sense, it's so. But here you have. So I also display the fluctuations. So fluctuations are maximum at the transition point. So basically, this implies that at this point you have huge fluctuations. Basically, it means that you go from LR1 to LR2 like this, very fast. You're fluctuating a lot before you unbind. Okay. So now the question is, how general is two-state kinetics? Is it only within the selectin family of receptors, or it exists somewhere else? And then the second question is, what is the molecular origin of catch-sleep transition in cell adhesion bonds? And that may come, and that will come from computer simulations. So luckily for us, there was this paper in which they also performed experiments on L-selectin, not P-selectin, but another receptor molecule, similar but very different. I mean, similar in the sense that it has the same binding determinant, but it's coming from different cells, it's much longer, and then, they also played with another ligand, endoglycan, okay? And they also showed that this is our initial pair, P-selectin, PSGL1. That's the lifetime as a function of force. You can look at the distribution of lifetimes as a function of force as well. So this is how it's going to change. Okay, so you can think about the two-dimensional surface for the distribution of lifetimes. For L-selectins, they found similar transition, although you don't have it as sharp as in here. So in here from 0 to 0.7, in here you have it from 0 to 0.1. So it's not as sharp, but nonetheless, it's non-monotonic nonetheless, okay? And then for endoglycan, you have, again, not as sharp, but it's a similar transition. So it turns out that many molecules are actually exhibiting this catch-sleep, kind of dynamics of unbinding. So we also played with these two pairs, and now we know that, well, this is our initial landscape. This is the P-selectin, and this is the L-selectin, slightly different molecule, as I said before. But if you just look at this slice, you make a section of your landscape along the conformational transitions, conformational fluctuations. What you will see is that P-selectin to PSGL1, this state is very stable but wide. There's a huge distance to go from here to here. This one is unstable, less stable, but very narrow. Okay, it's 0.5 nanometers to go from here to the barrier top, and they differ in energy by, well, 5.2 minus 3.2, 2 kTs. If you go to this pair, now the unstable state is still unstable, but it's wider than the stable state here. And the difference, nonetheless, is 1.9. So very close difference between instability between this state and this state for this pair and for this pair. So it's 1.9 kT, okay? And now if you look at this guy, then this state becomes almost as stable as this state and becomes wider and wider and wider. And 5.3 minus 4.6, So it is 0.7 kg. Okay.